Hey everyone, ever look at a massive bridge or a towering crane and just wonder, how does that work? Well, it all comes down to forces. But here's the interesting part. What happens when those forces start pulling in all different directions? Today, we're going to build a visual guide to see exactly how they add up. Let's jump right in.
So, picture this. You've got two ropes tied to a hook. One person pulls one way, another person pulls a different way. Now, that hook doesn't feel two separate pulls, right? It feels one single combined force. The big question is, how do we figure out the exact strength and direction of that one force? That's the puzzle we're going to solve.
All right, here's our roadmap. We're going to build what I like to call a complete force toolkit. First, we'll get a handle on what a force actually is. Then we'll look at two really cool visual ways to add them together. After that, we'll get down to the nitty-gritty and calculate them with precision. We'll even learn how to take forces apart. And finally, we'll put the whole shebang together. Okay, first things first. Before we can even think about adding forces, we have to understand what we're dealing with. And this is the absolute key. A force is not just a simple number. It's something much more interesting. So at its heart, the idea is really simple. A force is just a push or a pull. You feel this stuff every single day, right? You push a door open, you pull a wagon. It's a physical, intuitive thing. But to really analyze it like an engineer, we need to get a little more specific. And here's why. A force has a magnitude. Are we talking about a gentle tap or a huge, powerful shove? It also has a direction. Is it going up, down, left, right, or at some specific angle? Anything that has both magnitude and direction is what we call a vector. And that changes everything, because you can't just add two vectors like you're adding 10 and 10. If they're pulling in different directions, 10 plus 10 is definitely not 20. So if regular old addition is off the table, how in the world do we add these force vectors? Well, the answer is actually pictures. We're going to use geometry. We have two fantastic visual methods to find the combined effect, which engineers call the resultant force. Our first method is the super cool parallelogram law. Imagine you have two forces. We'll call them F1 and F2, both starting from the exact same point. If you treat those two forces like the sides of a parallelogram and just kind of sketch in the other two sides to complete the shape, the diagonal line that cuts across that parallelogram, that's it. That's your resultant. It's a perfect visual of the single force that has the same effect as the other two combined. Now, the second method is the triangle rule, and I love this one. Think of it like you're following a map. First, you walk along the path of your first force, F1. Then, right where you stop, you immediately start walking along the path of the second force, F2. The resultant force, well, that's just the shortcut. It's the straight line from where you started your journey to where you finally ended up. You've made a triangle, and that closing side is your answer. So you might be looking at these two methods and thinking they look pretty different. But here's the secret. They're actually the same thing. A parallelogram is really just two of those triangles stuck together. So whether you use the parallelogram law or the triangle rule, it doesn't matter. You will always get the exact same resultant force. Same magnitude, same direction. Every single time. Okay, drawing pictures is awesome for understanding what's going on. I mean, it's super intuitive. But if you're actually building a bridge that people are going to drive on, kind of looks about right, isn't going to cut it. We need precision. We need exact numbers. And to get those numbers, we bring in a powerful friend, trigonometry. Let's go right back to that force triangle we made. We know the length of two sides, that's the strength of our two original forces, and we also know the angle between them. So our mission, should we choose to accept it, is to find the length of that third side, the magnitude of our resultant, and figure out its angle, which will give us its exact direction. So how do we find that missing side? Well, we use the perfect tool for the job, the law of cosines. I mean, this formula is literally tailor-made for this exact situation. If you've got any triangle and you know two sides and the angle between them, this formula will spit out the length of that third side. It's like magic. And when we plug in our numbers, let's say we have one force of 100 newtons and another of 120 newtons acting at some angle, we just run them through the law of cosines. And boom, we get a precise magnitude. No more guessing from a drawing. We get a hard number, something like 188 newtons. That is the exact strength of the combined pull. Awesome, we've got the magnitude. But remember, that's only half the story for a vector. We still need its direction. For that, we bring in our second trusty tool, The law of science. This rule is all about the relationship between the sides of a triangle and the angles opposite them. It's exactly what we need to figure out the rest of the angles in our force triangle. So, by applying the law of sines, we can solve for the angle of our resultant force. And now we have the complete picture. The final force has a magnitude of 188 newtons, and it's acting at a very specific angle of 46.2 degrees. We know exactly how strong it is, and we know exactly which way it's pointed. Problem solved. Okay, so we have totally mastered putting forces together. But what's really cool is that in engineering, it's often just as important to do the complete opposite, to take one single force and break it down into useful little pieces. This is called resolving a force. Think about it this way. Let's say you've got a force that's pulling diagonally, maybe at a 45-degree angle. That's fine. But what if you really need to know how much of that pull is going straight sideways and how much is going straight up? To find that out, we resolve that one diagonal force into its horizontal, or X, and vertical, or Y components. And this whole process is basically just our triangle rule, but in reverse. We start with the total force, which is now the hypotenuse, the long side of a right-angled triangle. The other two sides of that triangle are what we're looking for, the horizontal component and the vertical component. And with just a little bit of basic trig, we can calculate the exact strength of the force acting along each axis. All right, let's just take a step back for a second and look at what we've built here. We have put together an incredibly powerful, complete toolkit for understanding, combining, and deconstructing forces. You know, we started with the core idea that a force is a vector. We learned how to add them up visually with the parallelogram law and the triangle rule. Then we got serious and calculated them precisely with the law of cosines and the law of sines. And we even learned how to take them apart by resolving them into components. That right there is your complete workflow for force analysis. And this really is what it all boils down to. All of these diagrams, all these triangles and formulas, they're all designed to find one thing, that single real-world force that an object is actually experiencing. This isn't just some abstract math problem. This is the physics of what is actually happening. So I'll leave you with this question. The next time you see a suspension bridge, a construction crane, or even just a simple traffic light hanging from a wire, stop and take a closer look, because you now have the tools to see the invisible world of forces holding it all in balance. What are you going to see differently now? Thanks for watching.